Tantor Audio, a division of Recorded Books, presents What is Life? With Mind and Matter and Autobiographical Sketches by Erwin Schrödinger. Foreword by Roger Penrose. Narrated by Bob Sauer. Foreword. When I was a young mathematics student in the early 1950s, I did not read a great deal, but what I did read, at least if I completed the book, was usually by Erwin Schrödinger. I always found his writing to be compelling, and there was an excitement of discovery with the prospect of gaining some genuinely new understanding about this mysterious world in which we live. None of his writings possesses more of this quality than his short classic, What is Life?, which, as I now realize, must surely rank among the most influential of scientific writings in this century. It represents a powerful attempt to comprehend some of the genuine mysteries of life made by a physicist whose own deep insights had done so much to change the way in which we understand what the world is made of. The book's cross-disciplinary sweep was unusual for its time, yet it is written with an endearing, if perhaps disarming, modesty at a level that makes it accessible to non-specialists and to the young who might aspire to be scientists. Indeed, many scientists who have made fundamental contributions in biology, such as J.B.S. Haldane and Francis Crick, have admitted to being strongly influenced by, although not always in complete agreement with, the broad-ranging ideas put forward here by this highly original and profoundly thoughtful physicist. Like so many works that have had a great impact on human thinking, it makes points that, once they are grasped, have a ring of almost self-evident truth, yet they are still blindly ignored by a disconcertingly large proportion of people who should know better. How often do we still hear that quantum effects can have little relevance in the study of biology, or even that we eat food in order to gain energy? This serves to emphasize the continuing relevance that Schrödinger's What is Life has for us today. It is amply worth rereading. Roger Penrose, 8th of August, 1991. Preface. A scientist is supposed to have a complete and thorough knowledge at first hand of some subjects and, therefore, is usually expected not to write on any topic of which he is not a master. This is regarded as a matter of noblesse oblige. For the present purpose, I beg to renounce the noblesse, if any, and to be freed of the ensuing obligation. My excuse is as follows. We have inherited from our forefathers the keen longing for unified, all-embracing knowledge. The very name given to the highest institutions of learning reminds us that from antiquity and throughout many centuries the universal aspect has been the only one to be given full credit. But the spread, both in width and depth, of the multifarious branches of knowledge during the last 100-odd years has confronted us with a queer dilemma. We feel clearly that we are only now beginning to acquire reliable material for welding together the sum total of all that is known into a whole, but on the other hand, it has become next to impossible for a single mind fully to command more than a small specialized portion of it. I can see no other escape from this dilemma, lest our true aim be lost forever, than that some of us should venture to embark on a synthesis of facts and theories, albeit with second-hand and incomplete knowledge of some of them, and at the risk of making fools of ourselves. So much for my apology. The difficulties of language are not negligible. One's native speech is a closely fitting garment, and one never feels quite at ease when it is not immediately available and has to be replaced by another. My thanks are due to Dr. Inkster, Trinity College, Dublin, to Dr. Padraig Brown, St. Patrick's College, Maynooth, and last but not least, to Mr. S.C. Roberts. They were put to great trouble to fit the new garment on me, and to even greater trouble by my occasional reluctance to give up some original fashion of my own. Should some of it have survived the mitigating tendency of my friends, it is to be put at my door, not at theirs. The headlines of the numerous sections were originally intended to be marginal summaries, and the text of every chapter should be read in continuo. Erwin Schrödinger, Dublin, September 1944. Homo liber nulla de re minus quam de morte cogitat, et eius sapientia non mortis sed vitae meditatio est. Spinoza's Ethics, Part 4, Proposition 67. There is nothing over which a free man ponders less than death. His wisdom is to meditate not on death, but on life. Chapter 1. The Classical Physicist's Approach to the Subject. Cogito ergo sum, Descartes. The general character and the purpose of the investigation. This little book arose from a course of public lectures delivered by a theoretical physicist to an audience of about 400, which did not substantially dwindle, though warned at the outset that the subject matter was a difficult one and that the lectures could not be termed popular, even though the physicist's most dreaded weapon, mathematical deduction, would hardly be utilized. The reason for this was not that the subject was simple enough to be explained without mathematics, but rather that it was much too involved to be fully accessible to mathematics. Another feature which at least induced a semblance of popularity was the lecturer's intention to make clear the fundamental idea which hovers between biology and physics to both the physicist and the biologist. For actually, in spite of the variety of topics involved, the whole enterprise is intended to convey one idea only, one small comment on a large and important question. In order not to lose our way, it may be useful to outline the plan very briefly in advance. The large and important and very much discussed question is, how can the events in space and time which take place within the spatial boundary of a living organism be accounted for by physics and chemistry? The preliminary answer, which this little book will endeavor to expound and establish, can be summarized as follows. The obvious inability of present-day physics and chemistry to account for such events is no reason at all for doubting that they can be accounted for by those sciences. Statistical physics, the fundamental difference in structure. That would be a very trivial remark if it were meant only to stimulate the hope of achieving in the future what has not been achieved in the past. But the meaning is very much more positive, that is to say, that the inability up to the present moment is amply accounted for. Today, thanks to the ingenious work of biologists, mainly of geneticists, during the last 30 or 40 years, enough is known about the actual material structure of organisms and about their functioning to state that, and to tell precisely why, present-day physics and chemistry could not possibly account for what happens in space and time within a living organism. The arrangements of the atoms in the most vital parts of an organism and the interplay of these arrangements differ in a fundamental way from all those arrangements of atoms which physicists and chemists have hitherto made the object of their experimental and theoretical research. Yet the difference which I have just termed fundamental is of such a kind that it might easily appear slight to anyone except a physicist who is thoroughly imbued with the knowledge that the laws of physics and chemistry are statistical throughout. For it is in relation to the statistical point of view that the structure of the vital parts of living organisms differs so entirely from that of any piece of matter that we physicists and chemists have ever handled physically in our laboratories or mentally at our writing desks. It is well nigh unthinkable that the laws and regularities thus discovered should happen to apply immediately to the behavior of systems which do not exhibit the structure on which those laws and regularities are based. The non-physicist cannot be expected even to grasp, let alone to appreciate the relevance of, the difference in statistical structure stated in terms so abstract as I have just used. To give the statement life and color, let me anticipate what will be explained in much more detail later, namely that the most essential part of a living cell, the chromosome fiber, may suitably be called an aperiodic crystal. In physics, we have dealt hitherto only with periodic crystals. To a humble physicist's mind, these are very interesting and complicated objects. They constitute one of the most fascinating and complex material structures by which inanimate nature puzzles his wits. Yet compared with the aperiodic crystal, they are rather plain and dull. The difference in structure is of the same kind as that between an ordinary wallpaper in which the same pattern is repeated again and again in regular periodicity, and a masterpiece of embroidery, say a Raphael tapestry, which shows no dull repetition, but an elaborate, coherent, meaningful design traced by the great master. In calling the periodic crystal one of the most complex objects of his research, I had in mind the physicist proper. Organic chemistry, indeed, in investigating more and more complicated molecules, has come very much nearer to that aperiodic crystal which, in my opinion, is the material carrier of life, and therefore it is small wonder that the organic chemist has already made large and important contributions to the problem of life, whereas the physicist has made next to none. The naive physicist's approach to the subject. After having thus indicated very briefly the general idea, or rather the ultimate scope of our investigation, let me describe the line of attack. I propose to develop first what you might call a naive physicist's ideas about organisms, that is, the ideas which might arise in the mind of a physicist who, after having learnt his physics and, more especially, the statistical foundation of his science, begins to think about organisms and about the way they behave and function, and who comes to ask himself conscientiously whether he, from what he has learnt, from the point of view of his comparatively simple and clear and humble science, can make any relevant contributions to the question. It will turn out that he can. The next step must be to compare his theoretical anticipations with the biological facts. It will then turn out that, though on the whole his ideas seem quite sensible, they need to be appreciably amended. In this way we shall gradually approach the correct view, or, to put it more modestly, the one that I propose as the correct one. Even if I should be right in this, I do not know whether my way of approach is really the best and simplest. But, in short, it was mine. The naive physicist was myself, and I could not find any better or clearer way towards the goal than my own crooked one. Why are the atoms so small? A good method of developing the naive physicist's ideas is to start from the odd, almost ludicrous question, why are atoms so small? To begin with, they are very small indeed. Every little piece of matter handled in everyday life contains an enormous number of them. Many examples have been devised to bring this fact home to an audience, none of them more impressive than the one used by Lord Kelvin. Suppose that you could mark the molecules in a glass of water, then pour the contents of the glass into the ocean, and stir the latter thoroughly so as to distribute the marked molecules uniformly throughout the 7 seas. If then you took a glass of water anywhere out of the ocean, you would find in it about 100 of your marked molecules. The actual sizes of atoms lie between 1/5000th and 1/2000th of the wavelength of yellow light. The comparison is significant because the wavelength roughly indicates the dimensions of the smallest grain still recognizable in the microscope. Thus, it will be seen that such a grain still contains thousands of millions of atoms. Now, why are atoms so small? Clearly, the question is an evasion, for it is not really aimed at the size of the atoms. It is concerned with the size of organisms, more particularly with the size of our own corporeal selves. Indeed, the atom is small when referred to our civic unit of length, say the yard or the meter. In atomic physics, one is accustomed to use the so-called angstrom, which is the 10 to the 10th part of a meter, or in decimal notation, 0.00000000001 meter. Atomic diameters range between 1 and 2 angstroms. Now those civic units in relation to which the atoms are so small are closely related to the size of our bodies. There is a story tracing the yard back to the humor of an English king whom his counselors asked what unit to adopt, and he stretched out his arm sideways and said, "Take the distance from the middle of my chest to my fingertips. That will do all right." True or not, the story is significant for our purpose. The king would naturally indicate a length comparable with that of his own body, knowing that anything else would be very inconvenient. With all his predilection for the angstrom unit, the physicist prefers to be told that his new suit will require 6.5 yards of tweed, rather than 65,000 millions of angstroms of tweed. It thus being settled that our question really aims at the ratio of two lengths, that of our body and that of the atom, with an incontestable priority of independent existence on the side of the atom, the question truly reads, why must our bodies be so large compared with the atom? I can imagine that many a keen student of physics or chemistry may have deplored the fact that every one of our sense organs, forming a more or less substantial part of our body and hence, in view of the magnitude of the said ratio, being itself composed of innumerable atoms, is much too coarse to be affected by the impact of a single atom. We cannot see or feel or hear the single atoms. Our hypotheses with regard to them differ widely from the immediate findings of our gross sense organs and cannot be put to the test of direct inspection. Must that be so? Is there an intrinsic reason for it? Can we trace back this state of affairs to some kind of first principle in order to ascertain and to understand why nothing else is compatible with the very laws of nature? Now this, for once, is a problem which the physicist is able to clear up completely. The answer to all the queries is in the affirmative. The working of an organism requires exact physical laws. If it were not so, if we were organisms so sensitive that a single atom or even a few atoms could make a perceptible impression on our senses, heavens, what would life be like? To stress one point, an organism of that kind would most certainly not be capable of developing the kind of orderly thought which, after passing through a long sequence of earlier stages, ultimately results in forming, among many other ideas, the idea of an atom. Even though we select this one point, the following considerations would essentially apply also to the functioning of organs other than the brain and the sensorial system. Nevertheless, the one and only thing of paramount interest to us in ourselves is that we feel and think and perceive. To the physiological process which is responsible for thought and sense, all the others play an auxiliary part, at least from the human point of view, if not from that of purely objective biology. Moreover, it will greatly facilitate our task to choose for investigation the process which is closely accompanied by subjective events, even though we are ignorant of the true nature of this close parallelism. Indeed, in my view, it lies outside the range of natural science and very probably of human understanding altogether. We are thus faced with the following question: why should an organ like our brain, with the sensorial system attached to it, of necessity consist of an enormous number of atoms in order that its physically changing state should be in close and intimate correspondence with a highly developed thought? On what grounds is the latter task of the said organ incompatible with being, as a whole or in some of its peripheral parts which interact directly with the environment, a mechanism sufficiently refined and sensitive to respond to and register the impact of a single atom from outside? The reason for this is that what we call thought, 1, is itself an orderly thing, and 2, can only be applied to material, that is, to perceptions or experiences, which have a certain degree of orderliness. This has 2 consequences. First, of physical organization, to be in close correspondence with thought, as my brain is with my thought, must be a very well-ordered organization, and that means that the events that happen within it must obey strict physical laws, at least to a very high degree of accuracy. Secondly, the physical impressions made upon that physically well-organized system by other bodies from outside obviously correspond to the perception and experience of the corresponding thought, forming its material, as I have called it. Therefore, the physical interactions between our system and others must, as a rule, themselves possess a certain degree of physical orderliness. That is to say, they too must obey strict physical laws to a certain degree of accuracy. Physical laws rest on atomic statistics and are therefore only approximate. And why could all this not be fulfilled in the case of an organism composed of a moderate number of atoms only, and sensitive already to the impact of one or a few atoms only? Because we know all atoms to perform all the time a completely disorderly heat motion which, so to speak, opposes itself to their orderly behavior and does not allow the events that happen between a small number of atoms to enroll themselves according to any recognizable laws. Only in the cooperation of an enormously large number of atoms do statistical laws begin to operate and control the behavior of these assemblées with an accuracy increasing as the number of atoms involved increases. It is in that way that the events acquire truly orderly features. All the physical and chemical laws that are known to play an important part in the life of organisms are of this statistical kind. Any other kind of lawfulness and orderliness that one might think of is being perpetually disturbed and made inoperative by the unceasing heat motion of the atoms. Their precision is based on the large number of atoms intervening. First example, paramagnetism. Let me try to illustrate this by a few examples, picked somewhat at random out of thousands, and possibly not just the best ones to appeal to a reader who is learning for the first time about this condition of things, a condition which in modern physics and chemistry is as fundamental as, say, the fact that organisms are composed of cells is in biology, or as Newton's law in astronomy, or even as the series of integers 1, 2, 3, 4, 5 in mathematics. An entire newcomer should not expect to obtain from the following few pages a full understanding and appreciation of the subject, which is associated with the illustrious names of Ludwig Boltzmann and Willard Gibbs, and treated in textbooks under the name of statistical thermodynamics. If you fill an oblong quartz tube with oxygen gas and put it into a magnetic field, you find that the gas is magnetized. The magnetization is due to the fact that the oxygen molecules are little magnets and tend to orientate themselves parallel to the field, like a compass needle. But you must not think that they actually all turn parallel, for if you double the field, you get double the magnetization in your oxygen body, and that proportionality goes on to extremely high field strengths, the magnetization increasing at the rate of the field you apply. This is a particularly clear example of a purely statistical law. The orientation the field tends to produce is continually counteracted by the heat motion, which works for random orientation. The effect of this striving is, actually, only a small preference for acute over obtuse angles between the dipole axes and the field. Though the single atoms change their orientation incessantly, they produce on the average, owing to their enormous number, a constant small preponderance of orientation in the direction of the field and proportional to it. This ingenious explanation is due to the French physicist P. Langevin. It can be checked in the following way. If the observed weak magnetization is really the outcome of rival tendencies, namely the magnetic field, which aims at combining all the molecules parallel, and the heat motion, which makes for random orientation, then it ought to be possible to increase the magnetization by weakening the heat motion, that is to say, by lowering the temperature, instead of reinforcing the field. That is confirmed by experiment, which gives the magnetization inversely proportional to the absolute temperature, in quantitative agreement with theory, Curie's law. Modern equipment even enables us, by lowering the temperature, to reduce the heat motion to such insignificance that the orientating tendency of the magnetic field can assert itself, if not completely, at least sufficiently to produce a substantial fraction of complete magnetization. In this case, we no longer expect that double the field strength will double the magnetization, but that the latter will increase less and less with increasing field, approaching what is called saturation. This expectation, too, is quantitatively confirmed by experiment. Notice that this behavior entirely depends on the large numbers of molecules which cooperate in producing the observable magnetization. Otherwise, the latter would not be constant at all, but would, by fluctuating quite irregularly from one second to the next, bear witness to the vicissitudes of the contest between heat motion and field. Second example, Brownian movement, diffusion. If you fill the lower part of a closed glass vessel with fog, consisting of minute droplets, you will find that the upper boundary of the fog gradually sinks with a well-defined velocity, determined by the viscosity of the air and the size and the specific gravity of the droplets. But if you look at one of the droplets under the microscope, you find that it does not permanently sink with constant velocity, but performs a very irregular movement, the so-called Brownian movement, which corresponds to a regular sinking only on the average. Now, these droplets are not atoms, but they are sufficiently small and light to be not entirely insusceptible to the impact of one single molecule of those which hammer their surface in perpetual impacts. They are thus knocked about and can only on the average follow the influence of gravity. This example shows what funny and disorderly experience we should have if our senses were susceptible to the impact of a few molecules only. There are bacteria and other organisms so small that they are strongly affected by this phenomenon. Their movements are determined by the thermic whims of the surrounding medium. They have no choice. If they had some locomotion of their own, they might nevertheless succeed in getting from one place to another, but with some difficulty, since the heat motion tosses them like a small boat in a rough sea. A phenomenon very much akin to Brownian movement is that of diffusion. Imagine a vessel filled with a fluid, say water, with a small amount of some colored substance dissolved in it, say potassium permanganate, not in uniform concentration, but rather where dots indicate the molecules of the dissolved substance, permanganate, and the concentration diminishes from left to right. If you leave this system alone, a very slow process of diffusion sets in, the permanganate spreading in the direction from left to right, that is, from the places of higher concentration towards the places of lower concentration, until it is equally distributed through the water. The remarkable thing about this rather simple and apparently not particularly interesting process is that it is in no way due, as one might think, to any tendency or force driving the permanganate molecules away from the crowded region to the less crowded one, like the population of a country spreading to those parts where there is more elbow room. Nothing of the sort happens with our permanganate molecules. Every one of them behaves quite independently of all the others, which it very seldom meets. Every one of them, whether in a crowded region or in an empty one, suffers the same fate of being continually knocked about by the impacts of the water molecules, and thereby gradually moving on in an unpredictable direction, sometimes towards the higher, sometimes towards the lower concentrations, sometimes obliquely. The kind of motion it performs has often been compared with that of a blindfolded person on a large surface imbued with a certain desire of walking, but without any preference for any particular direction, and so changing his line continuously. That this random walk of the permanganate molecules, the same for all of them, should yet produce a regular flow towards the smaller concentration, and ultimately make for uniformity of distribution, is at first sight perplexing, but only at first sight. If you contemplate thin slices of approximately constant concentration, the permanganate molecules which in a given moment are contained in a particular slice will, by their random walk, it is true, be carried with equal probability to the right or to the left. But precisely in consequence of this, a plane separating two neighboring slices will be crossed by more molecules coming from the left than in the opposite direction, simply because to the left there are more molecules engaged in random walk than there are to the right. And as long as that is so, the balance will show up as a regular flow from left to right, until a uniform distribution is reached. When these concentrations are translated into mathematical language, the exact law of diffusion is reached in the form of a partial differential equation, which I shall not trouble the reader by explaining, though its meaning in ordinary language is again simple enough. The reason for mentioning the stern mathematically exact law here is to emphasize that its physical exactitude must nevertheless be challenged in every particular application. Being based on pure chance, its validity is only approximate. If it is, as a rule, a very good approximation, that is only due to the enormous number of molecules that cooperate in the phenomenon. The smaller their number, the larger the quite haphazard deviations we must expect, and they can be observed under favorable circumstances. Third example, limits of accuracy of measuring. The last example we shall give is closely akin to the second one, but has a particular interest. A light body suspended by a long thin fiber in equilibrium orientation is often used by physicists to measure weak forces which deflect it from that position of equilibrium, electric, magnetic, or gravitational forces being applied so as to twist it around the vertical axis. The light body must, of course, be chosen appropriately for the particular purpose. The continued effort to improve the accuracy of this very commonly used device of a torsional balance has encountered a curious limit, most interesting in itself. In choosing lighter and lighter bodies and thinner and longer fibers to make the balance susceptible to weaker and weaker forces, the limit was reached when the suspended body became noticeably susceptible to the impacts of the heat motion of the surrounding molecules and began to perform an incessant irregular dance about its equilibrium position, much like the trembling of the droplet in the second example. Though this behavior sets no absolute limit to the accuracy of measurements obtained with the balance, it sets a practical one. The uncontrollable effect of the heat motion competes with the effect of the force to be measured and makes the single deflection observed insignificant. You have to multiply observations in order to eliminate the effect of the Brownian movement of your instrument. This example is, I think, particularly illuminating in our present investigation. For our organs of sense, after all, are a kind of instrument. We can see how useless they would be if they became too sensitive. The square root n rule. So much for examples for the present. I will merely add that there is not one law of physics or chemistry of those that are relevant within an organism or in its interactions with its environment that I might not choose as an example. The detailed explanation might be more complicated, but the salient point would always be the same, and thus the description would become monotonous. But I should like to add one very important quantitative statement concerning the degree of inaccuracy to be expected in any physical law, the so-called square root n law. I will first illustrate it by a simple example and then generalize it. If I tell you that a certain gas under certain conditions of pressure and temperature has a certain density, and if I express this by saying that within a certain volume of a size relevant for some experiment, there are under these conditions just n molecules of the gas, then you might be sure that if you could test my statement in a particular moment of time, you would find it inaccurate, the departure being of the order of square root n. Hence, if the number n equals 100, you would find a departure of about 10, thus relative error equals 10%. But if n equals 1 million, you would be likely to find a departure of about 1,000, thus relative error equals 1/10%. Now, roughly speaking, this statistical law is quite general. The laws of physics and physical chemistry are inaccurate within a probable relative error of the order of 1 divided by square root n, where n is the number of molecules that cooperate to bring about that law, to produce its validity within such regions of space or time or both that matter, for some considerations or for some particular experiment. You see from this again that an organism must have a comparatively gross structure in order to enjoy the benefit of fairly accurate laws, both for its internal life and for its interplay with the external world. For otherwise, the number of cooperating particles would be too small, the law too inaccurate. The particularly exigent demand is the square root. For though 1,000,000 is a reasonably large number, an accuracy of just 1 in 1,000 is not overwhelmingly good if a thing claims the dignity of being a law of nature. Chapter 2. The hereditary mechanism. Das Sein ist ewig, denn Gesetze bewahren die lebendigen Schätze, aus welchen sich das All geschmückt. Being is eternal, for laws there are to conserve the treasures of life on which the universe draws for beauty. Goethe. The classical physicist's expectation, far from being trivial, is wrong. Thus we have come to the conclusion that an organism and all the biologically relevant processes that it experiences must have an extremely many atomic structure and must be safeguarded against haphazard single atomic events attaining too great importance. That, the naive physicist tells us, is essential so that the organism may, so to speak, have sufficiently accurate physical laws on which to draw for setting up its marvelously regular and well-ordered working. How do these conclusions, reached biologically speaking a priori, that is, from the purely physical point of view, fit in with actual biological facts? At first sight, one is inclined to think that the conclusions are little more than trivial. A biologist of, say, 30 years ago might have said that, although it was quite suitable for a popular lecturer to emphasize the importance, in the organism as elsewhere, of statistical physics, the point was in fact rather a familiar truism. For, naturally, not only the body of an adult individual of any higher species, but every single cell composing it contains a cosmical number of single atoms of every kind, and every particular physiological process that we observe, either within the cell or in its interaction with the environment, appears, or appeared 30 years ago, to involve such enormous numbers of single atoms and single atomic processes that all the relevant laws of physics and physical chemistry would be safeguarded, even under the very exacting demands of statistical physics in respect of large numbers. This demand I illustrated just now by the square root n rule. Today we know that this opinion would have been a mistake. As we shall presently see, incredibly small groups of atoms, much too small to display exact statistical laws, do play a dominating role in the very orderly and lawful events within a living organism. They have control of the observable large-scale features which the organism acquires in the course of its development. They determine important characteristics of its functioning, and in all this, very sharp and very strict biological laws are displayed. I must begin with giving a brief summary of the situation in biology, more especially in genetics. In other words, I have to summarize the present state of knowledge in a subject of which I am not a master. This cannot be helped, and I apologize particularly to any biologist for the dilettante character of my summary. On the other hand, I beg leave to put the prevailing ideas before you more or less dogmatically. A poor theoretical physicist could not be expected to produce anything like a competent survey of the experimental evidence, which consists of a large number of long and beautifully interwoven series of breeding experiments of truly unprecedented ingenuity on the one hand, and of direct observations of the living cell conducted with all the refinement of modern microscopy on the other. The hereditary code script, chromosomes. Let me use the word pattern of an organism in the sense in which the biologist calls it the four-dimensional pattern, meaning not only the structure and functioning of that organism in the adult or in any other particular stage, but the whole of its ontogenetic development from the fertilized egg cell to the stage of maturity when the organism begins to reproduce itself. Now, this whole four-dimensional pattern is known to be determined by the structure of that one cell, the fertilized egg. Moreover, we know that it is essentially determined by the structure of only a small part of that cell, its nucleus. This nucleus, in the ordinary resting state of the cell, usually appears as a network of chromatin distributed over the cell. But in the vitally important processes of cell division, mitosis and meiosis, see below, it is seen to consist of a set of particles, usually fiber-shaped or rod-like, called the chromosomes, which number 8 or 12, or in man 48. But I ought really to have written these illustrative numbers as 2 times 4, 2 times 6, and continuing the series through 2 times 24, and so on, and I ought to have spoken of 2 sets in order to use the expression in the customary meaning of the biologist. For though the single chromosomes are sometimes clearly distinguished and individualized by shape and size, the 2 sets are almost entirely alike. As we shall see in a moment, one set comes from the mother, egg cell, one from the father, fertilizing spermatozoon. It is these chromosomes, or probably only an axial skeleton fiber of what we actually see under the microscope as the chromosome, that contain in some kind of code script the entire pattern of the individual's future development and of its functioning in the mature state. Every complete set of chromosomes contains the full code, so there are, as a rule, 2 copies of the latter in the fertilized egg cell, which forms the earliest stage of the future individual. In calling the structure of the chromosome fibers a code script, we mean that the all-penetrating mind, once conceived by Laplace, to which every causal connection lay immediately open, could tell from their structure whether the egg would develop, under suitable conditions, into a black cock or into a speckled hen, into a fly or a maize plant, a rhododendron, a beetle, a mouse, or a woman, to which we may add that the appearances of the egg cells are very often remarkably similar. And even when they are not, as in the case of the comparatively gigantic eggs of birds and reptiles, the difference is not so much in the relevant structures as in the nutritive material which in these cases is added for obvious reasons. But the term code script is, of course, too narrow. The chromosome structures are at the same time instrumental in bringing about the development they foreshadow. They are law code and executive power, or to use another simile, they are architect's plan and builder's craft in one. Growth of the body by cell division, mitosis. How do the chromosomes behave in ontogenesis? The growth of an organism is effected by consecutive cell divisions. Such a cell division is called mitosis. It is, in the life of a cell, not such a very frequent event as one might expect, considering the enormous number of cells of which our body is composed. In the beginning, the growth is rapid. The egg divides into 2 daughter cells, which, at the next step, will produce a generation of 4, then of 8, 16, 32, 64, etc., etc. The frequency of division will not remain exactly the same in all parts of the growing body, and that will break the regularity of these numbers. But from their rapid increase we infer by an easy computation that on the average as few as 50 or 60 successive divisions suffice to produce the number of cells in a grown man, or say 10 times the number, taking into account the exchange of cells during lifetime. Thus, a body cell of mine is, on the average, only the 50th or 60th descendant of the egg that was I. In mitosis, every chromosome is duplicated. How do the chromosomes behave on mitosis? They duplicate. Both sets, both copies of the code, duplicate. The process has been intensively studied under the microscope and is of paramount interest, but much too involved to describe here in detail. The salient point is that each of the 2 daughter cells gets a dowry of 2 further complete sets of chromosomes exactly similar to those of the parent cell. So all the body cells are exactly alike as regards their chromosome treasure. However little we understand the device, we cannot but think that it must be in some way very relevant to the functioning of the organism, that every single cell, even a less important one, should be in possession of a complete double copy of the code script. Some time ago we were told in the newspapers that in his African campaign, General Montgomery made a point of having every single soldier of his army meticulously informed of all his designs. If that is true, as it conceivably might be considering the high intelligence and reliability of his troops, it provides an excellent analogy to our case, in which the corresponding fact certainly is literally true. The most surprising fact is the doubleness of the chromosome set maintained throughout the mitotic divisions. That it is the outstanding feature of the genetic mechanism is most strikingly revealed by the one and only departure from the rule, which we have now to discuss. Reductive division, meiosis, and fertilization, syngamy. Very soon after the development of the individual has set in, a group of cells is reserved for producing at a later stage the so-called gametes, the sperma cells or egg cells, as the case may be, needed for the reproduction of the individual in maturity. Reserved means that they do not serve other purposes in the meantime and suffer many fewer mitotic divisions. The exceptional or reductive division, called meiosis, is the one by which eventually, on maturity, the gametes are produced from these reserved cells, as a rule only a short time before syngamy is to take place. In meiosis, the double chromosome set of the parent cell simply separates into 2 single sets, one of which goes to each of the 2 daughter cells, the gametes. In other words, the mitotic doubling of the number of chromosomes does not take place in meiosis. The number remains constant, and thus every gamete receives only half, that is, only 1 complete copy of the code, not 2. For example, in man, only 24, not 2 times 24 equals 48. Cells with only 1 chromosome set are called haploid, from Greek single. Thus the gametes are haploid, the ordinary body cells diploid, from Greek double. Individuals with 3, 4, or generally speaking with many chromosome sets in all their body cells occur occasionally. The latter are then called triploid, tetraploid, and so on up to polyploid. In the act of syngamy, the male gamete, spermatozoon, and the female gamete, egg, both haploid cells, coalesce to form the fertilized egg cell, which is thus diploid. One of its chromosome sets comes from the mother, one from the father. Haploid individuals. One other point needs rectification. Though not indispensable for our purpose, it is of real interest, since it shows that actually a fairly complete code script of the pattern is contained in every single set of chromosomes. There are instances of meiosis not being followed shortly after by fertilization, the haploid cell, the gamete, undergoing meanwhile numerous mitotic cell divisions, which result in building up a complete haploid individual. This is the case in the male bee, the drone, which is produced parthenogenetically, that is, from non-fertilized and therefore haploid eggs of the queen. The drone has no father. All its body cells are haploid. If you please, you may call it a grossly exaggerated spermatozoon, and actually, as everybody knows, to function as such happens to be its one and only task in life. However, that is perhaps a ludicrous point of view, for the case is not quite unique. There are families of plants in which the haploid gamete, which is produced by meiosis and is called a spore in such cases, falls to the ground and, like a seed, develops into a true haploid plant comparable in size with a diploid. The leafy lower part of a moss is the haploid plant called the gametophyte because at its upper end it develops sex organs and gametes, which by mutual fertilization produce in the ordinary way the diploid plant, the bare stem with a capsule at the top. This is called the sporophyte because it produces by meiosis the spores in the capsule at the top. When the capsule opens, the spores fall to the ground and develop into a leafy stem, etc. The course of events is appropriately called alternation of generations. You may, if you choose, look upon the ordinary case, man and the animals, in the same way, but the gametophyte is then, as a rule, a very short-lived unicellular generation, spermatozoon or egg cell as the case may be. Our body corresponds to the sporophyte. Our spores are the reserved cells from which, by meiosis, the unicellular generation springs. The outstanding relevance of the reductive division. The important, the really fateful event in the process of reproduction of the individual is not fertilization, but meiosis. One set of chromosomes is from the father, one from the mother. Neither chance nor destiny can interfere with that. Every man owes just half of his inheritance to his mother, half of it to his father. That one or the other strain seems often to prevail is due to other reasons which we shall come to later. Sex itself is, of course, the simplest instance of such prevalence. But when you trace the origin of your inheritance back to your grandparents, the case is different. Let me fix attention on my paternal set of chromosomes, in particular on one of them, say number 5. It is a faithful replica either of the number 5 my father received from his father or of the number 5 he had received from his mother. The issue was decided by a 50-50 chance in the meiosis taking place in my father's body in November 1886 and producing the spermatozoon, which a few days later was to be effective in begetting me. Exactly the same story could be repeated about chromosomes numbers 1, 2, 3, and so forth through to 24 of my paternal set, and mutatis mutandis about every one of my maternal chromosomes. Moreover, all the 48 issues are entirely independent. Even if it were known that my paternal chromosome number 5 came from my grandfather, Joseph Schrödinger, the number 7 still stands an equal chance of being either also from him or from his wife Marie, née Bogner. Crossing over, location of properties. But pure chance has been given even a wider range in mixing the grandparental inheritance in the offspring than would appear from the preceding description, in which it has been tacitly assumed, or even explicitly stated, that a particular chromosome as a whole was either from the grandfather or from the grandmother. In other words, that the single chromosomes are passed on undivided. In actual fact, they are not, or not always. Before being separated in the reductive division, say the one in the father's body, any two homologous chromosomes come in close contact with each other, during which they sometimes exchange entire portions. By this process, called crossing over, two properties situated in the respective parts of that chromosome will be separated in the grandchild, who will follow the grandfather in one of them, the grandmother in the other one. The act of crossing over, being neither very rare nor very frequent, has provided us with invaluable information regarding the location of properties in the chromosomes. For a full account, we should have to draw on conceptions not introduced before the next chapter, for example, heterozygosy, dominance, etc. But as that would take us beyond the range of this little book, let me indicate the salient point right away. If there were no crossing over, two properties for which the same chromosome is responsible would always be passed on together, no descendant receiving one of them without receiving the other as well. But two properties due to different chromosomes would either stand a 50-50 chance of being separated, or they would invariably be separated, the latter when they were situated in homologous chromosomes of the same ancestor, which could never go together. These rules and chances are interfered with by crossing over. Hence, the probability of this event can be ascertained by registering carefully the percentage composition of the offspring in extended breeding experiments suitably laid out for the purpose. In analyzing the statistics, one accepts the suggestive working hypothesis that the linkage between two properties situated in the same chromosome is the less frequently broken by crossing over the nearer they lie to each other. For then there is less chance of the point of exchange lying between them, whereas properties located near the opposite ends of the chromosomes are separated by every crossing over. Much the same applies to the recombination of properties located in homologous chromosomes of the same ancestor. In this way, one may expect to get from the statistics of linkage a sort of map of properties within every chromosome. These anticipations have been fully confirmed. In the cases to which tests have been thoroughly applied, mainly but not only Drosophila, the tested properties actually divide into as many separate groups, with no linkage from group to group, as there are different chromosomes, 4 in Drosophila. Within every group, a linear map of properties can be drawn up which accounts quantitatively for the degree of linkage between any two out of that group, so that there is little doubt that they actually are located, and located along a line as the rod-like shape of the chromosome suggests. Of course, the scheme of the hereditary mechanism, as drawn up here, is still rather empty and colorless, even slightly naive, for we have not said what exactly we understand by a property. It seems neither adequate nor possible to dissect into discrete properties the pattern of an organism which is essentially a unity, a whole. Now, what we actually state in any particular case is that a pair of ancestors were different in a certain well-defined respect, say one had blue eyes, the other brown, and that the offspring follows in this respect either one or the other. What we locate in the chromosome is the seat of this difference. We call it in technical language a locus, or if we think of the hypothetical material structure underlying it, a gene. Difference of property, to my view, is really the fundamental concept rather than property itself, notwithstanding the apparent linguistic and logical contradiction of this statement. The differences of properties actually are discrete, as will emerge in the next chapter when we have to speak of mutations, and the dry scheme hitherto presented will, as I hope, acquire more life and color. Maximum size of a gene. We have just introduced the term gene for the hypothetical material carrier of a definite hereditary feature. We must now stress 2 points which will be highly relevant to our investigation. The first is the size, or better, the maximum size of such a carrier. In other words, to how small a volume can we trace the location. The second point will be the permanence of a gene, to be inferred from the durability of the hereditary pattern. As regards the size, there are 2 entirely independent estimates, one resting on genetic evidence, breeding experiments, the other on cytological evidence, direct microscopic inspection. The first is, in principle, simple enough. After having, in the way described above, located in the chromosome a considerable number of different, large-scale features, say of the Drosophila fly, within a particular one of its chromosomes, to get the required estimate we need only divide the measured length of that chromosome by the number of features and multiply by the cross-section. For, of course, we count as different only such features as are occasionally separated by crossing over, so that they cannot be due to the same microscopic or molecular structure. On the other hand, it is clear that our estimate can only give a maximum size because the number of features isolated by genetic analysis is continually increasing as work goes on. The other estimate, though based on microscopic inspection, is really far less direct. Certain cells of the Drosophila, namely those of its salivary glands, are for some reason enormously enlarged, and so are their chromosomes. In them you distinguish a crowded pattern of transverse dark bands across the fiber. C.D. Darlington has remarked that the number of these bands, 2,000 in the case he uses, is, though considerably larger, yet roughly of the same order of magnitude as the number of genes located in that chromosome by breeding experiments. He inclines to regard these bands as indicating the actual genes or separations of genes. Dividing the length of the chromosome, measured in a normal-sized cell by their number, 2,000, he finds the volume of a gene equal to a cube of edge 300 angstroms. Considering the roughness of the estimates, we may regard this to be also the size obtained by the first method. Small numbers. A full discussion of the bearing of statistical physics on all the facts I am recalling, or perhaps I ought to say of the bearing of these facts on the use of statistical physics in the living cell, will follow later. But let me draw attention at this point to the fact that 300 angstroms is only about 100 or 150 atomic distances in a liquid or in a solid, so that a gene contains certainly not more than about 1 million or a few million atoms. That number is much too small, from the square root n point of view, to entail an orderly and lawful behavior according to statistical physics, and that means according to physics. It is too small even if all these atoms played the same role as they do in a gas or in a drop of liquid. And the gene is most certainly not just a homogeneous drop of liquid. It is probably a large protein molecule in which every atom, every radical, every heterocyclic ring plays an individual role, more or less different from that played by any of the other similar atoms, radicals, or rings. This, at any rate, is the opinion of leading geneticists such as Haldane and Darlington, and we shall soon have to refer to genetic experiments which come very near to proving it. Permanence. Let us now turn to the second highly relevant question. What degree of permanence do we encounter in hereditary properties, and what must we therefore attribute to the material structures which carry them? The answer to this can really be given without any special investigation. The mere fact that we speak of hereditary properties indicates that we recognize the permanence to be almost absolute. For we must not forget that what is passed on by the parent to the child is not just this or that peculiarity, a hooked nose, short fingers, a tendency to rheumatism, hemophilia, dichromacy, etc. Such features we may conveniently select for studying the laws of heredity. But actually, it is the whole four-dimensional pattern of the phenotype, the visible and manifest nature of the individual, which is reproduced without appreciable change for generations, permanent within centuries, though not within tens of thousands of years, and born at each transmission by the material structure of the nuclei of the two cells which unite to form the fertilized egg cell. That is a marvel, than which only one is greater, one that, if intimately connected with it, yet lies on a different plane. I mean the fact that we, whose total being is entirely based on a marvelous interplay of this very kind, yet possess the power of acquiring considerable knowledge about it. I think it possible that this knowledge may advance to little short of a complete understanding of the first marvel. The second may well be beyond human understanding.